Okay, so we'll talk about the second law of thermodynamics. I won't do any derivations, but I'll just give you the punchline on stuff. I want you to understand it physically, what's happening. Okay, so if you are familiar with the these terms, irreversible processes and entropy, that's the new function we are introducing in this chapter. Okay, you might have heard of entropy. It's a state function, and it measures the disorder in the system. Okay? So just like energy is a state function, pressure is a state function, entropy is a state function. Okay? It turns out that you can easily find the energy of a system, the absolute value. You can find the pressure of a system. You can find the temperature of a system. It's very hard to calculate the entropy of this gas, for instance. Okay? But what we'll show you is, so what we will be happy with this, and again, whenever you draw PV diagram, you're dealing with a gas. It's hard to do the entropy for a given state, but we can give you formula for the change in entropy. Okay? So that's what we'll show you. Okay. Again, entropy is a state function. It measures the disorder in a system. Okay. It also tells you, okay, so what is the main point of energy?
To do work.
To do work, very good. Entropy tells you how much of the energy is not available to do work. Entropy tells you how much of the money in your bank you can't spend. Okay. All right. So we'll talk about the second law of thermodynamics. Okay. And then we'll talk about engines and refrigerators, heat engines and refrigerators. Okay. Of course, and then we'll talk about their efficiencies. Okay. So here's the 4 laws of thermodynamics. The 0th law just says if you have 2 objects in thermal contact and they're not exchanging any net heat, then they're at the same temperature. The first law of thermodynamics is a conservation of energy principle. With heat taken into account. You know, when we were kids, we learned about conservation of mechanical energy, then we graduated to conservation of all forms of energy. Okay, so first law of thermodynamics is conservation of energy principle with heat taken into account. It's a harder thing to do. Okay, so you have the 0th law, first law, then we came up with the second law. When do you need a new law?
When something's unaccounted for.
I'm sorry?
When something's unaccounted for.
When these guys cannot explain all the phenomena that you observe, then you need another law. And then after you come up with this law, if you observe new phenomena that these guys cannot explain, then you would need another law, and so on. Okay? So now let me show you a phenomenon that occurs which these two guys cannot explain. Okay? So let's do that. So that'll be a justification for needing this second law of thermodynamics. Okay? All right, so let's say here's the room, and the room is at 30 degrees Celsius. The air in the room is at 30 degrees Celsius. And you got a bunch of ice from your refrigerator, which was at minus 5 degrees Celsius. You come back half an hour later. What has happened? I'm sorry? The ice is melted. Okay. And if it's a big room, the water, everything is at 30 degrees Celsius. We'll 29.5 degrees Celsius. What really happened? All that happened was heat went from here to there. What was the total energy of the system? I'm sorry? Well, heat went from here to here, but the total energy of this system was equal to the total energy of this system. Energy was conserved. Okay. Now let's do the following. So this happens. This never happens. Well, this energy is equal to this energy. Energy is still conserved. But this process never happens. You put a glass of water in there, and it doesn't automatically freeze on its own. Okay? And the room doesn't get warmer. Okay? Heat could have flown from here to there, and this could have frozen. Energy conservation is not violated here. The zeroth and the first law is not violated here or here. But you observe this phenomenon in nature and not this one. So now you need a second law, you need another law that tells you why this is possible and this is not possible. Again, that's the second law of thermodynamics. Okay, so the second law of thermodynamics postulates a quantity called entropy. And what the second law says is, in nature, only processes where entropy increases occur. So for this process, entropy increases. For this process, entropy decreases. And so you don't see this process. And that's the second law. Okay, when entropy decreases, order has increased. Okay. So when entropy decreases, see, in a solid, the molecules are more arranged in order, so order has increased. And so this process doesn't occur. Okay. So again, we've learned two things. We've learned why do you need new laws? You need new laws when existing laws cannot explain the phenomena that you observe. Okay? So here's a phenomenon that I'm showing you that the first law of thermodynamics cannot explain. Okay? The fact that this process only occurs this way and not backwards. Okay? For instance, I mean, you intuitively knew this, the ice melting, you're fine. If I recorded that and played that movie backwards, you'd say something is wrong with that thing, right? No. You'll intuitively know that that's not possible.
Does this also relate to like the whole theory of like time zero?
I'm sorry?
Does this also relate to the arrow of time?
Narrow time, yep. Mm-hmm. So increase in entropy also tells you the arrow of time, okay? All right, now that we know why we need that, okay, so let's go ahead and talk about that. So if you pour hot water into a glass and place the glass on a table, the water will slowly cool, okay? You'd be astonished if the water got warmer and the room cooled, okay? So and so we need a new physical principle that is required to explain why processes occur in one direction and not the other, where energy would be conserved in both directions. Okay. So here's another example, a warm cup and ice, and the ice melts, okay, but you never see the opposite process, okay, even though energy would be conserved. Okay, so again, what is the explanation? In this case, entropy increases. In this case, entropy would decrease. That's the second law of thermodynamics. Okay. Okay, I'm going to, so we've talked about this before. A reversible process is one in which the system and the environment can be returned to their initial conditions. Okay, so this ice melting is an irreversible process because there's no way you can return this system to that. Well, don't we freeze water? Yes, we freeze water. If you can freeze water by doing work, you'll learn later in the chapter, you can freeze this water by doing work. But then that work generates heat. And so when you go back to here, what ends up happening is that cup is warmer. You cannot go back to the state where it's 40 degrees Celsius. Okay? So that's an irreversible process. A reversible process is one in which the system and the environment can be returned to their initial condition. All naturally occurring processes are known to be irreversible. Okay, you put a pizza in an oven, what happens? In an oven that is on or that's warm. You cook the pizza. After it's cooked, you can remove heat from the pizza, but you won't uncook it. Yeah. All right, so again, so the second law states in one way, there's a quantity called entropy, and in processes that you observe in nature, only processes where entropy increases occur. Okay? In reversible processes, entropy will remain constant. But reversible processes are ideal processes, frictionless processes, and they don't occur in nature. Okay? So they will provide limits for you for understanding stuff. Okay? In all natural processes, entropy increases. So entropy is a measure of disorder in the system. Entropy is a state function. Okay? So for instance, on a PV diagram, for an ideal gas, entropy just depends on the state of your system. Change in entropy, okay, for a state function, okay, so let's say this is the initial entropy, okay. Let's say you go from this initial state to that final state. You can calculate the change in entropy. How about if you go from here to there? What is the change in entropy? Exactly, very good. So for a state function, the change in value of that function is path independent. Okay? And that was true for, so the change in pressure, temperature, volume, energy, entropy is path independent. Okay? Can you tell me any quantity that is path dependent? Heat absorbed and? Very good. Okay? So there are two quantities that are path dependent. Okay? And again, calculating this entropy for a state is very hard to do. Okay, so in all engineering fields, you never calculate that. Now, physicists will try to do that, but that's again a hard thing to do. We'll show you how to calculate the change in entropy. Okay, so change in entropy in terms of the heat gained or lost and the temperature of the system. So here is the basic formula. So change in entropy, an infinitesimal change in entropy is an infinitesimal amount of heat absorbed by the system divided by the temperature at which it absorbed the heat. Temperature is in Kelvin scale, and so when the heat is absorbed by the system, change in entropy is positive. When the heat is given up by the system, this is negative, and change in entropy is negative. Okay, so that's the definition. This is a way to calculate in terms of the possible number of microstates for a given macrostates of the system. Okay, so this formula lets you calculate the absolute value of entropy. This is the number of microstates. That's the Boltzmann's constant, and that's the entropy. So what we are essentially saying is this is almost impossible to calculate for most systems. It's a very hard problem. Okay? So you can calculate here's the formula for the entropy, but again, in practice, we don't do that. All right. Entropy is a measure of how much energy is not available to do work. Okay, again, your whole purpose of energy was to be able to do work. And here is something that tells you how much energy you cannot use to work. Okay? And so I can give you an extreme example. So if you had a gas at infinite temperature, there's zero work you can get out of it. Okay? So to extract work from heat, you would need a high temperature reservoir and a low temperature reservoir. So if you have a reservoir at infinite temperature, well, you can't get heat to flow from here, this guy, to anywhere else. So this is at infinite temperature and it's got infinite energy, but it's of no use. It's like Bill Gates might be a trillionaire, it's no use to me.
Is that why
Yeah.
work is 100% efficient converting that into heat?
Yeah, so heat is the worst form of energy. You can convert any other form of energy to heat. Okay. So entropy is a measure of how much energy is not available to do work. Okay. All right, so the next couple of slides are as follows. When do we do PV diagrams? When you have a system that is a gas. Okay. So we just told you that, okay, so this is the change in entropy for an infinitesimal process. ds is dq by t. And the integral just means how much entropy changed when you went from this point to that point. Okay. Entropy, here is the initial entropy, here is the final entropy. Let's say you have this system go from this point to that point. Now what we'll show you is if these 2 points are along they fall on an isothermal curve, we'll give you the formula initially. Okay? And then we'll give you a formula for a more general transformation. Okay? So that'll be next. So right now we'll keep things simple and we'll give you a formula for the change in entropy when you're going along an isothermal curve. Okay? And here is a typical example that is used to illustrate that. Okay? This, you can't do this in real life, but anyway. So let's say you have a yeah, but theory is good, you know. I mean, you understand the concept of infinity, right? You can never get there, but it's a useful concept. All right, so here's vacuum. You take a gas, and you let this gas expand through a valve into this. Okay, when this gas is expanding, okay, when I lift this guy up, I'm doing work. Okay. I'm doing work because I had to apply force against the gravitational force. If I was in space and there was no force on it, I move it, yeah, okay, and if it moves at constant velocity, okay. Now, when the gas, so in your car, when the piston expands, it has to push against atmosphere, and so it did work. Now, this gas is expanding into vacuum. It's not pushing anything, it's not working. And by the way, you're not absorbing any heat. And since it did not do any work, it's not spending any energy. So the temperature of this gas doesn't change. All that happened was its volume increased. Okay? All right, let's say you have your clothes in your drawer. You go take them out and throw them all over the room. Do you have more disorder?
Yes.
Yeah. There is more entropy here. So it wasn't, well, the process when this expansion happened was some crazy curve like this. You ended up there. But well, we know that the temperature doesn't change. What is the change in entropy along this path? The same as along this path. So we're going to calculate the entropy along this path. And that's the trick. Okay. All right. Temperature, pressure, and volume of a gas fluctuate unpredictably during an irreversible process. Okay, during this process. Our entropy is a state function. The integral can be evaluated along a reversible path, which will be the isothermal path. Okay. So, for this free expansion, those 2 points lie on an isotherm. So here's how you calculate the entropy. Okay, during an isothermal process, change in internal energy is 0. So dq is equal to dw. Okay, any heat absorbed goes into doing the work. Change in entropy is that divided by that. The work done by a gas in an infinitesimal process is pressure times dV. P is nRT over V, and so if you do that, the T cancels. Here's what you get. So this is the formula. That is the change in entropy when you go along an isotherm. Okay, so if 2 points are connected by an isotherm, there's the formula for the change in entropy. Yeah. Well, you guys are tough customers. Now, if you ask me what is the change in entropy if this is the process, if these are the 2 points, now I'll give you the formula. Okay. So this formula is when the temperature does not change, only along an isotherm. When the temperature and volume both change, here is the formula for the change in entropy. Change in entropy when both the temperature and volume change. And you see that previous formula, this formula is a special case of this formula. This formula is when T final is equal to T initial, log of 1 is 0, this term drops out. All right, so there's the change in entropy for an ideal gas. So what we have done is we've given you this formula, PV. So for any state, the change in entropy in going from anywhere to anywhere for an ideal gas is given by this formula. Okay? The temperature can change and the volume can change. If you're along an isotherm, the temperature doesn't change and this guy drops off. If you're in an isochoric process, the volume doesn't change and this drops off. Okay. So if you're going straight up and down, this term is 0 and only that term is. Okay. So now you have a way to calculate the change in entropy for any process, for an ideal gas. Okay. So the second law of thermodynamics states the entropy of a system and its surrounding, so the universe, increases during irreversible processes. All processes in nature are irreversible, so entropy always increases and remains constant during reversible processes. Okay? It never decreases. Okay, I'm just